Chapter 2, Part 3, Curved Space and Spacetime. The ability to map the behavior of space or spacetime using metric descriptions like those you were introduced to in the previous section is essential for astrophysics and cosmology. A metric helps to define the shortest distance between any two locations, which is important for understanding how light travels across the universe. Although the Minkowski metric applies to many useful situations, it is not the only metric we need to consider if we want to be able to tackle the subject of cosmology. The key insight of Einstein's theory of general relativity was a connection between gravity and geometry. To describe the universe and its expansion, including the behavior of light under the influence of gravity, it is necessary to extend our description of geometry and metrics to encompass curvature of space and time. Flat and curved geometries. To introduce curved, i.e., non Euclidean geometries, we start by taking a step back from the discussion of spacetime and consider further the geometry of two and three dimensional spaces. In the mathematical field of differential geometry, the type of smoothly varying spaces we will explore and we will explore and refer to as manifolds. We'll use both manifold and geometric shape interchangeably. In three dimensions, we have an intuitive idea of the difference between a flat and curved surface. A piece of paper on a desk has a flat geometry. The surface of a balloon or a globe cannot be flattened in such a way as to lie flat on a desk and still retain the original distances between points and angles between lines. Does the surface of a cylinder have a flat or curved geometry? The surface of a cylinder has a flat geometry. A cylinder tube can be unrolled to form a flat surface without distorting the relationships between points on its surface. An intrinsically curved surface, such as the surface of a sphere, cannot be flattened in this way. For example, consider how maps of the world become distorted in flat projections. Whether a particular surface manifold is flat or curved can be determined mathematically. To explore this, we will consider the metric that describes the surface of a sphere. Spherical coordinates are commonly used in physics because they simplify the mathematics of problems that are spher- spherically symmetric. Figure 2.10 shows how the three-dimensional spherical coordinates r, theta, and phi are defined. They are related to x, y, and z Cartesian coordinates as follows: x equals r sine theta cos phi, y equals r sine theta sine phi, and z equals r cos theta. Figure 2.10, the 3D relationship between spherical and Cartesian coordinates. The length of a line element in three-dimensional space is given by dl squared equals dx squared plus dy squared plus dz squared. Using the relations above, it is possible to show that this is equivalent to dl squared equals dr squared plus r squared d theta squared plus r squared sine squared d phi squared. Last term again is r squared sine theta squared d phi squared. Equation 2.15. The surface of a sphere corresponds to the situation where r equals big R, where big R is a constant. In other words, we consider locations on a surface to be at a fixed distance r from the origin, as shown in figure 2.11. Arc of the length r theta. A circle C of constant theta coordinate drawn on the surface of a sphere. In this geometry, dr equals 0 because r equals constant. And so the metric for this geometry can be described by the line element dl squared equals r squared d theta squared plus r squared sine theta squared d phi squared. Because r is a constant, differentiating to r equals 0, or the difference in r equals 0. How many dimensions does the space described by the metric in equation 2.16 have? It describes a 2D space. The two variables theta and phi are the only dimensions. The third spatial dimension, the freedom to move in the r direction, does not exist in this geometry. In the following example, we will consider how the geometry described by the equation 2.16 affects the properties of circles. Example 2.6. Consider the circle C drawn on the upper half of the surface of the sphere in figure 2.11, which has its center at the North Pole. Every point on the circle has the same value of theta. Use the concept of a line element and the metric of a spherical surface to derive an expression for the circumference of the circle C. Solution. Because theta is constant, difference in theta equals 0, and so the line element that represents an infinitesimal distance on the sphere's surface reduces to dl squared equals r squared sine theta squared d phi squared. The circumference of C is the sum of all the infinitesimal distances around the circle. So it's given by the integral of the line element summed over all values of phi, the angle around the circle, which in radians ranges from 0 to 2 pi. This gives C equals integral of d 2 pi 0 to 2 pi of dl, which equals to 0 to 2 integral of 0 to 2 pi of r sine theta d phi, which equals to r sine theta phi 2 pi to 0, which equals to 2 pi r sine theta, integrating with respect to phi. Considering the same circle C defined on the surface of the sphere shown in figure 2.11, what is its radius? Remembering that the circle is defined on the curved surface with its center at the North Pole, the radius is the length of the arc shown in the figure, which means r times theta. If the surface had the same flat geometry as a plane, we would accept the circumference to be 2 pi times radius, i.e. 2 pi r theta, whereas the example found a circumference of 2 pi r sine theta. So the circumference on the curved surface is smaller than that of a circle in flat space. This makes intuitive sense if we consider figure 2.11 again, focusing now on the circle around the equator. Its circumference is simply 2 pi r because theta equals pi over 2, and so sine theta equals 1. But the circle's radius as drawn on the surface is the arc from the North Pole to the equator, which is clearly much longer than r. Hopefully, you are now persuaded that geometrical relationships differ in curved geometries. The reason for this is that the geometry determines the shortest distance between 2 points. known as geodesic. In flat space, the geodesic is always a straight line, but when movement is confined to a curved surface, the shortest route between 2 points on that surface always has to account for its curvature. In the case of the surface of a sphere, shortest paths are always part of a great circle. A great circle, a circle defined by the intersection of the surface with a plane that passes through the surface's sphere's center. For example, the Earth's equator. Another example you may have come across is great circle aeroplane flight paths, which trace the shortest route between 2 points on the Earth's surface, but can seem surprising when shown on a map that is a flat projection of the globe. If you have studied observational astronomy previously, you will have encountered similar ideas in the context of astronomical coordinate systems defined on the celestial sphere. The next exercise explores an example of distances in curved geometries. Exercise 2.4. The cities of Calgary and Brussels are both at latitude of 51 degree north and separated in longitude by 108 degrees. The shortest great circle distance between the two cities is 7,300 kilometers, which involves a route that passes over Greenland, Iceland, and the very north of Scotland. Calculate the distance between the two cities if instead a route that follows the 51-degree latitude line is taken, which would pass through eastern Canada and southern England, and comment on how the two distances compare. Solution to exercise 2.4. The distance along a path on the surface of a sphere can be calculated by integrating the line element dl along a parametrization of the path. For a line of constant latitude, this is very similar to the calculation in example 2.6 because lines of latitude have a constant angle theta. If the coordinate system is defined as in figure 2.11, so that the angle phi corresponds to longitude and theta corresponds to 90 degree minus the latitude value, the distance L is therefore given by L equals integration of phi 1 to phi 2 r sine theta with respect to phi, where phi 1 and phi 2 are the start and end values of longitude. When r equals 6,370 kilometers is the average radius of the Earth, we need to work with angles in radians, and so theta equals 90 minus 51 equals 39, which corresponds to 0.681 radians. The actual longitude angles were not provided, but the location of the zero value doesn't affect the calculation, so we can find phi 1 equals 0 and phi 2 equals 118, which equals to 2.06 radians. Solving the integral as in example 2.6 gives L equals r sine theta with respect to phi 2 minus phi 1, which gives r sine theta phi 2, which equals to 6,370 kilometers multiplied by sine of 0.68 sine 0.681 multiplied by 2.06, which equals to 8,260 kilometers. So the distance along the route at fixed latitude is 8,260 kilometers, which is around 13% longer than the Great Circle distance of 7,300 kilometers. Figure 2.12 illustrates three ways in which curved 2D spaces, such as those of spherical or saddle shaped surfaces, behave differently to flat ones. These differences concern the relation between the circumference and the radius of circle, labels C and B respectively in the diagram. The geometry of triangles, the behavior of initially parallel lines. The figure also shows that it is possible to identify two different directions in which curved geometry can deviate from that of flat surface. Non-planar surfaces can have positive curvature or negative curvature, typically parameterized by a curvature parameter k. In positively curved 2D spaces, k is greater than 0. The interior angles of triangles sum to greater than 180-degree circumference of circles are smaller, and lines of shortest distance geodesics that are initially parallel may converge. In negatively curved 2D spaces where k is smaller than 0, the interior angles of triangles sum to less than 180-degree. Circumferences of circles are larger, and initially parallel geodesics may diverge. Flat where k equals 0, initially parallel lines remain parallel. The angles of a triangle add up to 180 degrees. The circumference of a circle equals 2 pi r, or b instead of r. Positive curvature where k is greater than 0. The angles of a triangle are greater than 180 degree. The circumference of a circle is less than 2 pi r or 2 pi beta, 2 pi b. Initially parallel lines converge. Scenario C, where negative curvature k is less than 0, the angles of a triangle is less than 180 degree. The circumference of circle C is greater than 2 pi b. Initially parallel lines diverge. Figure 2.12, differences in geometry of 2D spaces. A flat space, B a space with positive curvature, C a space with a negative curvature. Similar deviations from Euclidean geometry occur for 3D and 4D curved spaces and have important implications for the behavior of light and so for our understanding of spacetime in cosmology. So far in part 3 of chapter 2, we've looked at flat and curved geometry and how, depending on the curvature, the parallel lines may converge or diverge, angles of a triangle may change, the circumference could be smaller or bigger, again, depending on curvature. Looking at curved 2D spaces. Defining and measuring curvature. How can curvature be measured? First, consider a curved line as shown in figure 2.13. Use the geometric information in figure 2.13 to determine whether the line is most curved at point A, B, or C. Briefly explain your reasoning. The line is curved at A than at B or C. The line deviates the most over a short distance from the straight tangent line, whereas at C the curve remains closest over a large distance to a straight tangent line. Figure 2.13, a line with varying curvature marked with points A, B, and C. Figure 2.13 also shows that a line segment that is more curved can be approximated at a particular location by a segment of a circle of smaller radius, whereas a less curved line requires a circle of much larger radius to approximate its shape. Compare the lengths of lines RA and RC. This leads to the curvature kx at point X being defined as the inverse of the radius of a circle that best matches the curve at that location. The more curved it is, the smaller the radius r. Exercise 2.5. Question A. What shape is described by a line of constant curvature kx equals 0.2 per centimeter? Question B. What is the curvature kx of a straight line measured at any point x along it? Back to question A. What shape is described by a line constant curvature kx equals 0.2 centimeter per centimeter? We can use equation 2.17 to calculate the radius corresponding to the provided value of kx, where r equals 1 over k equals 1 over 0.2, which equals to 5 centimeters. Because the curvature and hence r are the same at all locations, the curve must be a circle of radius 5 centimeters. Part B question was, what is the curvature kx of a straight line measured at any point x along it? A straight line must have constant curvature, but however large a circle we draw tangential to the line, an even large circle will approximate the straight line better. The curvature of a straight line must therefore be smaller than 1 over r for all r. For cosmology, the curvature of both three-dimensional spaces and four-dimensional spacetime are relevant. These properties influence the paths taken by light and the distances between objects, such as galaxies, as the universe expands. We therefore need to define curvature in a way that can be applied to a variety of geometries in multiple dimensions. Figure 2.13 demonstrates that curvature is connected in some way to the behavior of tangent lines. Where the curvature is high, the slopes of the tangent lines change rapidly as small steps are taken along the curve, whereas for low curvature, the slopes do not change much as you move along the curve. In a 2D geometry, the slope is the first derivative of the coordinates, e.g. dy over dx, and so the rate at which the slope changes is the second derivative d squared y over dx squared. The derivatives are quantities that connect how different coordinates change in relation to each other, and they can be used to construct a definition of curvature that is intrinsic to the geometry being measured. This means that the curvature can be determined without making measurements in a higher dimensional space, in contrast to what is done in figure 2.13, where the 1D curve is investigated with 2D xy coordinates. Question: what is the mathematical entity that describes the intrinsic geometry of a particular space manifold? Answer: the intrinsic geometry of a manifold is described by its metric. Therefore, metric coefficients and their derivatives provide us with a way to determine the intrinsic curvature. In dimensional space, we can write the following non-intuitive expression for intrinsic curvature K in terms of metric coefficients and their derivatives. Non Note again the potential source of confusion that is in this context. Dx superscript 1 and dx superscript 2 indicate derivatives with respect to coordinates x superscript 1 and x superscript 2, but the superscript 2's in the final two terms indicate second derivative. Note again the potential source of confusion that in this context dx1 and dx2 indicate derivatives with respect to coordinates x1 and x2. Okay. met expression for intrinsic curvature k in terms of metric coefficients and their derivatives. K equals equation 2.18, where g mu mu refers to the metric elements as defined in equation 2.13, and its 1 and 2 labels refer to coordinates x1 equals x, x2 equals y for a 2D Cartesian geometry. For a subset of 2D metrics in G11 is constant and G22 depends only on x1. Equation 2.18 reduces to a simpler form, k equals 1 over equation 2.19. Question: what are G11 and G22 for a 2D planar for 2D plane polar geometry? Answer: referring back to example 2.5 from previous part, G11 equals 1 and is the metric coefficient for R. It is the multiplier of dr squared term in the line element form of the metric equation 2.10. G22 equals R squared and is the metric coefficient for theta, the multiplier of d theta squared term in the same form of the metric. Example 2.7. Find an expression for k theta phi for the surface of a sphere and show that the curvature does not depend on the coordinate location theta phi, i.e. that the curvature of a spherical surface is the same at every location. Show that theta phi does not make a difference to the curvature of a spherical surface by showing that it is the same at every location. Solution: the metric for the surface of a sphere is given by equation 2.16. dl squared equals r squared d theta squared plus r squared sine theta squared d difference in phi squared. To calculate k using equations 2.19, we need the two metric coefficients G11 and G22, where the 1 and 2 labels refer to theta and phi respectively. From equation 2.16, G11 equals r squared and G22 equals r squared sine theta squared. To evaluate the equation, we need to calculate the first and second derivatives of G22 with respect to x super 1, i.e. theta. dg22 over dx1 equals dg22 over d theta, which equals to 2r squared sine theta cos theta. And so the second derivative, we get 2r squared in brackets cos theta squared minus sine theta squared. Because equations 2.19 is algebraically messy, we will first work out each of its two terms individually. Substituting the first derivative of G22 into the first term in the equation gives that. Doing the same for the second term, dependent on the second derivative of G22, gives we can now use the two expressions above to find an expression for k, which simplifies to The first two terms cancel out and the final one simplifies further to give k equals 1 over r squared. You can see that in the end, after much algebra, the curvature of a spherical surface does not depend on the location of theta phi position. For the surface of a sphere of particular radius r, the curvature is the same everywhere and depends only on the surface's radius. Example 2.7 was intended to give you a flavor of the mathematical and physical meaning of spatial curvature. Curvature becomes even more complex to calculate for higher dimensional spaces. K is a simplified form of the Riemann curvature tensor R lambda mu rho mu, sometimes just referred to as Riemann tensor. Riemann tensor is a set of equation analogous to equation 2.18 that encapsulates the curvature at any location in a multi-dimensional space. Online resources: Riemannian geometry. The mathematical toolkit that underpins the theory of general relativity is Riemannian geometry. Our primary aim in this module is to develop and apply cosmological models, and so, although it is a fascinating topic, introducing the wealth of definitions and terminology required for a full discussion of Riemannian geometry is beyond our scope. The online resources for this chapter provide some additional information about the subject for interest only. The crucial point to take away, and the reason we have shown you the somewhat complicated form for the two-dimensional case is equation 2.18, is that like K, the curvature tensor is constructed entirely from derivatives of the metric coefficients. You will not be asked to calculate or manipulate it directly. The essential concept to remember from this section are summarized in the following box. Curvature of geometric spaces. Number one, curvature affects the shortest distance between 2 points in space. Number two, geometrical relationships such as the properties of circles and triangles differ in flat and curved spaces. 3. Curvature is an intrinsic property of a geometric space which can be determined at a given location in space if the metric is known. Number 4. Intrinsic curvature is determined from a combination of derivatives of the metric coefficients given for 2D geometries by equations 2.18. 5. The Riemann curvature tensor is a more complex combination of derivatives of metric coefficients. It encapsulates the curvature at any location of a manifold of arbitrary 10 dimensions, and so can be used to quantify curvature in the 3D and 4D situations relevant for general relativity and cosmology. So far, we have considered only spatial dimensions, but you have seen that special relativity requires us to work with four-dimensional spacetime, in which spatial and time dimensions can become intertwined. In the next section, we consider how the concept of curvature explored here can be applied to 4D spacetime. So far in part 3, after defining flat and curved surfaces and how where can be positive, negative, or flat, and the geometrical properties will change. We have looked at how to define and measure curvature using equations 2.18 and 2.19. Curved spacetime and geodesics. Curvature is an important concept in four-dimensional spacetime, as well as in the spatial geometries discussed so far. Although formally spacetime metrics are termed pseudo-Riemannian, a distinction not important for this module, the Riemann tensor and the arguments about curved geometries in the previous section can be applied to spacetime metrics as well as to purely spatial geometries. Curvature depends on combinations of the derivatives of metric components with respect to different coordinates. Considering the Minkowski metric, Equation 2.12. What basic statement must be true about any derivatives of its components? Answer. All of the components of the Minkowski metric are constants, either 1 or -1, and so their derivatives with respect to another coordinate must be 0. Because all of the partial derivatives of the components of its metric must be 0, we can conclude that Minkowski spacetime has zero curvature. It is a flat geometry. However, it is possible to construct spacetime geometries that are curved. And you will see in the next chapter that such geometries are a consequence of the theory of general relativity. Another concept from this chapter that is important to general relativity is the geodesic, the path of the shortest distance between 2 points for a particular metric, where distance is the spacetime invariant distance ds. Geodesics have the form of straight lines in flat Minkowski spacetime, but that take different forms in curved geometries such as the great circles around the Earth's surface. Geodesics can also be divided into three categories depending on the nature of the spacetime separation or metric interval between 2 points considered. Null geodesics are curves for which ds squared equals 0. For every interval along the curve, only particles traveling at the speed of light, i.e., photons, can travel along null geodesics, which are also known as light like geodesics. Time like geodesics are curves where ds squared is greater than 0. For every interval along the curve, the world lines of particles moving at v smaller than c must follow time-like paths. Space-like geodesics are curves where ds squared is smaller than 0 or negative for every interval along the curvature. These correspond to paths between events that are outside one another's light cones. Particles, including photons, cannot travel along a space-like path. Question. Can observers logically disagree about the order of two events that are connected by a geodesic that is 1 null, 2 time-like, and 3 space-like? Observers must agree about the order of events in situation where one event could be the physical cause of another. Therefore, two events that can be connected by null or time-like geodesics must have a fixed order for all observers. Observers may disagree, however, about the order of events for which the separation is space-like, because there can be no causal relationship between them if neither event is inside the other's light cone. The world lines along which particles travel are always time-like. The earlier discussion of special relativity implies that whether in flat or curved spacetime, observers in different reference frames may disagree about how quickly time elapses along those paths, i.e., how changes in the t coordinate along a path relate to changes in the other coordinates. In the next section, you will meet a definition of time that all observers in a region described by the same metric can agree on, a concept that will be essential for building geometric models of the universe. Proper time. Metrics are defined such that all observers can agree on the invariant spacetime interval between two events ds. An invariant time interval called the proper time dt can be defined in relation to the spacetime interval ds in a very simple way. D proper time equals ds over c. Because ds and c are both the same for all observers, proper time dt is a measure of time that everyone can agree on. It turns out that proper time has another useful property shown in the following example. Example 2.8. Consider a particle traveling along time-like geodesic in Minkowski, i.e. flat space. An observer who is not traveling with the particle sees it move a very short distance between two locations that have coordinates of x, y, z, x, a, y, a, z, a, and x, y, z, b in the observer's reference frame. Write down expressions for the proper time interval that elapses when the particle travels between these two locations, both in the reference frame of the observer and in the reference frame of the particle. Comment on how proper time relates to how time is perceived in the reference frame of a moving object. Solution. We start by writing down expression for the interval ds in the two reference frames. Firstly, for the observers, ds squared equals c squared dt squared minus difference in a coordinate squared minus difference in y coordinate squared minus difference in z coordinate squared. Where we have used equation 2.12, the Minkowski metric, and substitute the individual coordinate separations between events into the spatial separation terms. For the reference frame of the particle, we use primed notation to denote the different reference frames. We can immediately simplify this expression hugely because in the reference frame attached to the movable particle, its spatial coordinates do not change at all. It is at rest. So ds prime squared equals c squared dt prime squared. If we now apply equation 2.2 to the two expressions, we find that proper time squared equals dt squared minus difference in x coordinate squared minus difference in y coordinate squared minus difference in z coordinate squared over c squared, and proper time prime dt squared equals dt prime squared. The space-time separation is the same for both frames. ds equals ds prime, and so from the definition of proper time we can conclude that dt equals dt prime, which equals to dt prime. In other words, for a time-like world line, the proper time interval between two events on the world line is equivalent to the coordinate time interval dt measured in the frame at rest in relation to those events. The example provides a very useful result which can be generalized to apply to curved as well as flat spacetimes. Proper time and coordinate time. For events on the world line of a moving observer, meaning that they all occur at the same unchanging spatial coordinate location in the observer's frame, the proper time corresponds to the coordinate time that would be measured by a clock traveling with the observer. For an observer in a different reference frame, the proper time between events does not correspond to the coordinate time but can be determined from the metric based on the spatial coordinates of those events. The concept of proper time and its relation to coordinate time would be important for interpreting building and interpreting metric description of curved and flat spacetime in different regions of the universe. This is the topic of the next chapter.